So the attenuation coefficient is just a way of describing how much loss there is overall, depending on the frequency and how far you're going. That's all it is. So if we're imaging at 6 centimeters deep, yeah, you lose some decibels every centimeter. You hit a reflector and you lose decibels coming back, right? So if you're imaging 6 centimeters deep, the sound is traveling 12 centimeters, and so we've lost sound all the way through that. So energy is just absorbed every centimeter, okay? If we increase our frequency, we lose more. That's it. It's that simple. Now, those of you that were in the lab Monday and Tuesday have already seen me do the power and how we lose it going to the through a phantom. And you can certainly explain this to the people that have lab tomorrow. So feel free to tell them. But they'll see it tomorrow too. Okay. All right. Again, this is just restating our attenuation coefficient. So we've mentioned it, what, in 5 slides now? Maybe it's important. Okay. Maybe it's important. So in soft tissue, this is what it is, 0.5. Okay, so not just anything, but just soft tissue. As soon as you start looking at other tissues, muscle, bone, whatever, that number changes, okay? So if I gave you a question that said, at what depth would your signal lose half of its intensity? At what depth would your signal lose half of its intensity? I would have to tell you what the coefficient is, okay? I'd have to tell you what type of tissue you were going through. Now, the only one I want you to even think about assuming is a half a decibel per centimeter megahertz, okay? Anything else, I'll have to give it to you. If it's muscle, I'll have to say it's 1.0 decibels centimeter megahertz, okay? So if it's water, it'd be like 0.001. Whatever it is, I would have to give it to you, okay? So it wouldn't be much. Or you don't have to memorize these coefficients. What you do have to do is learn how to utilize this coefficient to calculate how much was lost in 6 centimeters, 5 centimeters. If I give you the intensity, you have to be able to calculate how far it goes before it loses like half its value. Okay. So you got to be able to utilize this, but you don't have to know the exact number. You don't have to memorize the number. Okay. All right, so attenuation in different media. Air has very high attenuation. If we go outside and I'm trying to talk to you across the parking lot, you're not going to hear it very well. You might need like air horns to communicate across great distances in parking lots. Has anyone ever tried that before? Yeah.
I'm not sure that the second half of this,
Yeah, I know.
oh, okay.
So when I post them, the notes will all be on the notes when they get posted at the end of the thing. I know it's not quite following along perfectly. I went back and I added some to chapter 6 after I posted them into Canvas. So.
Okay.
So you whip out that water-cooled pencil and start writing down. Okay. But like I did with the test review, I post, if you've noticed, I've been posting
Right.
all the notes as we go along. And if the battery on my iPad doesn't run out, then I'll post these too. All right, so fluids. So blood, for some reason, has an attenuation very similar to soft tissue. Not close to water, but more like soft tissue. Okay, we just go with it. Okay. Any questions about that? Okay, so this is what I was talking about, being able to calculate the depth of losing half your value of intensity. This is called the half value layer. How far do we have to go in any particular tissue to lose half of our energy? What's it going to depend on? Haley, what do you think it'll depend on? No, the other Haley. I wait to see who looks up first and then I pick the second one.
What was the question again?
What does the half value layer, what is it going to depend on? So this is the distance sound travels, and then it loses half its intensity.
It depends on the medium.
Okay, the medium, yes. It's absolutely going to depend on the medium. What else is it going to depend on?
The transducer.
The transducer. What part of the transducer? What property? Frequency, yeah. So it's going to depend on the medium and the frequency. Okay. You can see this. It says typically about 1/4 to 1 centimeter we lose half our value of our sound. That's pretty quickly. So you go down to 30 centimeters and you've lost a lot of halves. So other names that this goes by. So again, this becomes kind of that memorizing the new language sort of thing. Penetration depth, depth of penetration, same thing. Half boundary layer, okay? That's what they call the half value layer, the half boundary layer sometimes. Isn't it great that we have so many names for things in ultrasound? No? Why not?
So much to remember.
Oh, but it makes it easy. See, this way, if you're from the East Coast and you call everything half boundary layers, see, now they have to now learn it as the half value layer. The reason we have so many different names is our wonderful exam that we take, the ARDMS SPI exam, hasn't settled on vocabulary yet. They keep promising, but they haven't come up with the final vocabulary. So they have all these different names and they go by all of them. And so maybe someday they'll send out a memo that says this is the official vocabulary for ultrasound. We'll see.
So will they like use a variation of the same term throughout? It's like not consistent?
Yeah.
I feel like that's what he did on the test.
Amen, sister.
Okay. So half value layer depends on two factors, the media and the frequency of the transducer. All right, reflection and transmission. Okay, so reflection is key to imaging with ultrasound. If we don't get reflections back, we're not going to see anything, right? What color is assist? It's nothing, right? We're not getting any reflections back from the center of assist, so we just can't do anything with it, okay? So acoustic impedance is what's going to determine how much is reflected and how much is transmitted. Now, what the heck is acoustic impedance? Has anyone gone swimming You know how when you're in the water, you don't move as fast through water as like if you're running on the ground, right? You're impeded by the water, okay? Has anyone ever gone swimming in molasses? You can imagine it'd have a lot more impedance. There would be a huge impedance difference, right? So that's what the sound is doing. It's either swimming through soft tissue, or it's swimming through fat, or it's swimming through water. It's moving at different impedance as it moves through there. So the impedance is determined by both the density of the medium and the propagation speed, okay? And let me just kind of put this up on here. So we always refer to the impedance as, we use the unit Z, okay? So I'll make that a Z. That's the worst Z in the world. Let's do a better one. Z. Z equals the density times the propagation speed. There's your equation for Z. It's not real hard, okay? All right, let's go back to our slideshow. Okay, so impedance is determined by density and propagation speed. The impedance is a property of the medium only. It has nothing to do with the frequency, has nothing to do with, it has only to do with the density and the propagation speed, right? That's it, that's our impedance, period. Done. Now, the reflection that we get back from any tissue depends on the difference of impedance that it strikes at a boundary. Okay, what does that mean? Well, when the tissue is, okay, imagine if this is my tissue, right, that's high impedance. Everything bounces back, right? Now, imagine if we just had a, you know, I need to make one of these, hanging beads, right? And if I was to throw a bunch of erasers at a thing of hanging beads, some of them would bounce back and some of them would keep going. Okay, so that's less impedance. Okay? This has a lot of impedance, the hanging beads has less. And when you throw your eraser at it, some of them goes through and some of it comes back. See, that part that goes through is transmission. Okay, the part reflected back is reflection. Okay? Okay. When we talk about reflection and transmission, we're talking about impedance, and impedance is given in units of rails. Okay? Yeah.
So you're saying like the higher impedance, the more reflections you'll get?
Not necessarily, but in general,
Okay.
what really makes the impedance is the difference of impedance.
Okay.
So when I'm throwing my eraser at that wall of beads,
Right.
it's going through the air, and then the boundary is the beads, and so as it hits the boundary, some's reflected, some goes on. As I throw my eraser at the board here, it's the air impedance, the difference between the air and the board, that makes it completely reflect. So it's the difference of impedance at the boundary that gives you reflection. Boy, if only there was a way to use an equation to calculate what that difference would be. Wouldn't that be great? Okay, so impedance is in units of rails. Typically, the units are in megarails, 1 to 2 megarails for soft tissue, the difference in soft tissue. Now, your crystal on your ultrasound probe has an impedance of about 30 or 40 megarails. So there's a big difference between the impedance of the crystal in the body. And so one of the things we do is we use gel to even that out a little bit. Gel is sort of a middle impedance, but we call this the characteristic impedance, and this has to do with the tissues. So when we transmit into tissues, we're going to have this characteristic impedance And it's the differences of impedance that cause reflections to come back to our transducer and make our pictures. And what characterizes those differences is the tissue itself. And so our reflections are always characterizations of the tissue, what the tissue is made of. That's why ultrasound's so useful. We can actually see what the tissue's made of, or make a picture of the character of the tissue. If you look on a CT and you see a cyst, you can't tell if it's solid or cystic. It's just an area. And you use ultrasound and you go, oh, I know exactly what that is because the echoes coming back characterize that tissue for me. That's what this reflection is, okay? So let's look at reflection and transmission. So when a pulse strikes a boundary, if there's a difference of impedance, some of the sound comes back and some of it goes forward. Okay? And the percentage of the beam is given by the calculation. The percentage of the beam reflected is given by this equation down here that looks really worse than it is. Okay? And I think that equation is wrong. Ouch. Yeah, I need to make a little change to it here. Who put that in my slideshow? Okay. So somehow I messed up on the equation. Oh well. When I was putting it in here, where's my?
So look on your notes, you'll have it corrected.
Yeah, I don't know. I'm gonna write it out for you in just a second here, but I'm just really disappointed in myself that it's wrong on my slide here. Okay.
Did you say that these notes were on the module?
Yeah, they're on Canvas.
Okay.
So if you guys have been looking at the notes for the test results and how I calculated the test, it's the same. It's the same thing. I'm just doing these things and then I'm posting them onto Control X. And I'm posting them to YouTube. Excuse me. I'm trying to think and talk at the same time. Okay, there is the equation. That's the corrected version. Okay. Yeah, I'm posting the notes and the test review on YouTube, and I'm putting a link to it on Canvas. Okay, so instead of squaring each individual impedance, what you do is you square the difference. Okay, and is that what it looks like in your book?
Yeah.
Yeah, okay, good. Now, this equation looks difficult to work with, and it's not. Okay? All it says is that my difference of impedances, the square of my difference of impedances is what's reflected. Okay? Now, so here's why this is such a happy thing. I need to look in the book because I'm just trying to do this off the top of my head. Yeah, that's it. That's the one in the book. Okay. Just wanted to be sure. Okay, so let's do an example real quick of these impedances. So if we take our equation, right, the percentage reflected equals, and then that big hairy equation, which isn't so bad if I explain it to you, Z1 minus Z2 over Z2 plus Z1 quantity squared. And I did that wrong on purpose. Okay? And I did it wrong because it doesn't matter what order you put them in. As long as you got the minuses on top and the pluses on bottom, you're good. That's the difference of impedance. It doesn't matter if you go Z2 minus Z1. Okay, it's just the difference. And we're going to square it so that if you did it wrong like this, you'll come up with something that's like maybe a minus 4 over 16, or let's make it a number we can actually, minus 4 over 5 squared, okay? So if we put it in there backwards, what we end up getting when we square it is we still get 16 over 25, right? So it doesn't matter if you put Z1 or Z2 first, okay? Just put the minus on top and the plus on the bottom. Square it, whatever you get, times it by 100%, and you got it, okay? So this then becomes times 100%. And that gives you the percentage of reflected sound. Okay, so in this case it would be 16 over 25, which is, I don't know, close to 2/3 of it being reflected, something like that.
So are we gonna be given Z1 and Z2?
You'll probably be given Z1 and Z2, yeah. Or you'll be told that medium 1 has an impedance of 39 megarails and medium 2 has an impedance of 1 megarail. How much is reflected, how much is transmitted? Yeah, so I'm not going to tell you Z1 equals 39. You're gonna, if I tell you the impedance though, you're going to have to make that quantitative leap that, oh yeah, that's Z, okay? All right. Now sometimes we're not interested in how much is reflected, okay? So this is our reflected percentage. Pretty simple to do. If we just throw up some Z1s minus Z2s over Z1s plus Z2s. But sometimes we want to know what the percentage transmitted into the second boundary, second medium is. Anyone want to guess at how you do that? Basically.
Subtract from 100.
Yeah, that's right. You take 100% and you subtract what was reflected. Right? It has to equal whatever's left. 100% minus what was reflected is what went through. Okay? So the amount transmitted depends on the amount reflected. Should make sense. The amount reflected depends on the difference of impedance. Okay. So some sound goes back to the transducer and some continues on to the second medium. Are we all happy with this yet?
Very,
You are?
very happy.
Okay. Ingrid, how are you doing?
Better.
Okay.
I skimmed through the material, so this is making it more sense.
This makes sense?
Yeah.
Those of you in the back that can't see the equations on the bottom, you okay with it? All right. Marcus? Good. All right. How's it? Okay, I'll just move on. Okay, so let's talk about angle of incidence. Kind of getting to a whole new subject here. So we've already got our reflection. This is going to come into play a whole lot with transmission. All right? All right, so the angle of incidence is the angle at which the sound strikes a boundary. Okay, whatever that happens to be. Now, if it's a right angle of incidence, it's 90 degrees that it strikes it at. Anything else is considered an oblique angle of incidence. So normal incidence is what we call that 90 degrees. Alright, so if I throw it straight at the board, that's a 90-degree angle of incidence. Alright? Anything else is oblique. Alright? I'm going to draw you a couple of materials. Let's see, what's my film? Let's make it red. So there's one material, and let's do another one. Okay? We always measure the angle of incidence from, let's see, do I have lines on? No. I don't know how to make a line. Okay. Oops, that's not quite straight what I wanted to do. Let's see if we can do it better. Okay, so we always measure our angle of incidence from the normal line, okay? So 90 degrees is normal, right? And we had some other terms for it if we wanted to learn them, right? These are important, so we'll go. So 90 degrees is perpendicular, orthogonal, right? A right angle, 90 degrees, or the normal angle, okay? Lots of vocabulary to learn, right? Gosh, if only there was a mnemonic to help us learn that one. Yeah, I mean, perpendicular, orthogonal, right angle, 90 degrees. Everybody's familiar with geometry. Yeah. So let me go back to my drawing. Okay. So that is what we measure from. So whatever the angle is of the incident beam, if it's along that path, right, it has a zero angle, okay? So if it's a perpendicular incidence, it has a zero angle. Because the difference between that orthogonal, or that 90-degree angle, and our incident angle is zero. Now what if it's not? What if it's an oblique one? So it comes in like, that's a terrible drawing. Okay, like that. Okay? Again, like I said, we measure the angle from, I'm going to call it theta. We measure it from that normal incident angle. Okay? So whatever our actual angle in is, we measure it from that normal line. Good with that? Great. Okay. Now here's the fun part. the angle out is always equal to the angle in. They're always going to be the same. The reflected angle is always the same as the incident angle. Okay? Now I said reflected, not transmitted. Okay? So the angle out is always the same as the angle in, and we always measure it from the normal incidence. Now what's transmitted, who knows what angle that is? That's going to change depending on several factors. But the reflected angle is always the same as the incident angle. And where do we measure incident angles from?
90
From
degrees.
the perpendicular, right, from the 90 degrees. Okay. And remember, we're talking about our boundary being this boundary between two, whoops, where's my little, man. This thing's gonna drive me crazy. Oh, there it is. This boundary between our two media, okay? That's our boundary. And then our incidence coming in at either an angle or coming in straight. Okay. Yeah, I think you're right. I need to post these slides separate from just the review.
Can we go to the very last slide you were just on?
Yeah.
Is so, like, would that white space between the two of them,
That's the boundary.
is that the same thing as impedance?
The impedance is the property of each material. Okay? So
Interacting with what? Like water, air?
there's just, it's just a property of the material, like it's based on the speed of sound, so it's based on the stiffness and the density. That's the impedance. So, you know, if you've got, would be a good example of, so if you have molasses in the bottom of a cup, and you've got water on top of the molasses, and you drop a marble through it, it's gonna go quickly through the water and then hit the boundary and go slower through the molasses, right? That boundary between the two is what this whole thing represents. There shouldn't be a gap, but
Like oil and water or
Yeah.
something?
it's just the boundary between two substances.
Okay.
At that boundary, that's when the action happens. That's when reflections occur. Okay. All right, so at the boundary, when there's a difference of impedance, some of the sound is reflected and some of it's transmitted. Very simple. The amount reflected is given by the correct equation that I gave you earlier, not this one. This is again the incorrect one. For some reason, I don't know why I squared everything. No, it shouldn't be that. It's the difference squared. Do you want me to fix that, or are we good? Okay. So it's the difference squared is the amount reflected. The amount transmitted is just 100% minus the reflected. All right? And so we have that there. In general, very little is reflected through most tissues, okay? So that's just a little factoid for you to think about, yeah.
So, is this why blood vessels are anechoic? Because the blood is truly like one salt, like one substance, where like tissue and everything,
Yeah.
even though it's the same, it still has every cell has its own borders.
Yes.
Yeah.
Yes, so she said, is this why blood vessels are anechoic? Because they're homogeneous. They are truly a homogeneous tissue. blood cells in them are very, very small, and we really don't see them. There are circumstances where you will see them, but for the most part you don't see them. So there's no reflective surfaces, there's no boundaries between the blood vessels, and so nothing is reflected. That's absolutely true. Yeah. That's probably the only really truly homogeneous tissue in the body, I would guess. All right. All right, so I already covered the reflected angle, which is equal to the incident angle. So angle of incidence equals the angle of reflection. And again, this angle is always, always, always measured from our normal incidence, our normal angle, our perpendicular angle, our orthogonal, our right angle. Always measured from that. And I always refer to these angles as theta. So if you're not familiar with the, when I am writing these things out, I always write out a circle with a line through it. That is theta. Okay.
We were just
Now we're, like,
laughing.
trigonometry.
We had a
Physics professor that would.
He was like Indian or something,
Yeah.
and we had the class and he would say Tita, and we were like, what is Tita?
And the whole
And
class is
the
like
whole
looking
class.
at each other.
Yeah.
And that just reminded of us.
Yeah, so when I took calculus back in college, I had a Indian teaching assistant that taught us calculus, Calc 2, and he always talked about, well, whatever he talked about, I couldn't understand it.
Yeah, we could not understand.
I was totally lost, so I try to explain these things to you as I go along, so that you're not as lost as I was back then. It took me halfway through the semester, and I asked somebody, I said, what is he saying? I can't understand. They said, he's reading the book word for word.
Oh, no.
And I went, oh. After that, I did fine.
So that means normal line?
Hmm?
That means the normal line?
That just means an angle.
Oh, angle.
Angle. Theta is an angle. So in math and science, you usually have a couple of different things for angles. Phi is one of them. So if you see that little symbol, that's phi. Theta is the other. Sometimes they'll even do angles as alpha and gamma and beta. You'll see those sometimes. I tend to use theta almost exclusively. And if I have more than one angle I have to describe, I'll have theta 1 and theta 2. I keep it pretty simple. Okay. So if you hear me say theta, I'm talking about an angle or the difference between the normal line and the incident or reflected or transmitted, whatever. Okay? So, angle of incidence is always equal to the angle of reflection, and the angle is always measured from the normal incidence. Okay. Oops, I don't want to do that. Wrong button. Okay. Reflection and transmission with an oblique incidence. Okay. So, what we talked about before as far as reflection goes, we were talking about reflection with a normal incidence, okay? 0 degree variation from that normal line. It's coming in at 90 degrees, it hits the boundary, some of it's reflected, some of it's transmitted. Okay. Now let's talk about what happens when the angle is not quite perfectly 90 degrees. Okay? What's reflected is easy. Whatever the angle is in is the angle out, but in the opposite direction. Right? We're good with that? Good. Sometimes what is transmitted will be transmitted at a different angle, okay? And so that is called refraction. Didn't want to talk to you either. So refraction is a change in direction of the sound beam at a boundary. Okay. Now normally it's just transmitted at a different angle. There is something called the critical angle where sound could be completely absorbed just simply due to this refraction. Okay, we're not going to worry much more about that than what I just said there. Okay, there's something called a critical angle. We'll cover it. Don't worry. We'll get there. Okay. Oblique incidence is when the sound strikes the boundary at anything other than 90 degrees. Yeah. Should say 0 degrees, right? Because we always measure from the, yeah, so that should say 0 degrees. So it's just saying oblique incidence is when it strikes at something other than 90 degrees.
Yeah.
But again, we measure from that normal line, so that really should state 0 degrees. Because what we're measuring from is 90 degrees. Anyhow.
Just saying like the angle it hits, it makes a 90-degree angle.
No,
Or is it, you're talking about how it strays?
yeah, let me try to draw a line on the board here. Let's see. I don't know if this is going to work. Why did it do that to me? Say again?
Like on that one that you just put up with the dotted lines, the normal line is 0, so.
Yeah, let me go to that. I can't draw on these, I don't know why. Okay, so this is showing you that normal angle, right? We measure it from that, okay? So when I say, on the previous slide, when I said 90 degrees, you know, that'd be right along here, right? That's not what I meant. Along 0 degrees, along the angle of the normal angle. You're hitting the boundary at 90 degrees.
Yeah,
Okay.
yeah.
If this is the boundary.
Right.
You just want it to be perpendicular.
Yeah.
Perfectly.
Yeah. All right, so where was I? Okay, so the angle of incidence, okay, we already covered that. Moving on, okay. So, again, 100% is what's reflected plus what's transmitted. You didn't miss anything, trust me. Okay. The reflected angle is the easy one. It's always going to be equal to the incident angle, all right?
Yeah. And that's what's going on the board.
Yeah, that's what's happening on the blue side there. We're getting some reflected, we're getting some transmitted. Okay. If transmission occurs, sound can either go straight, the angle of transmission may increase, or it may decrease. That means it changed, right? Yeah, that's easy. Okay. If it changes direction, then we call that refraction. I already told you what refraction was a minute ago. It was the change of direction at a boundary, right? So this should be, you're already doing review. It's great. Okay. Now, there's two critical things you have to know about refraction. Refraction occurs if the incident angle is not 0 and the propagation speed in the two media are not equal. So, refraction occurs if, and only if, the angle is not zero, the incident angle, and the propagation speed is different. And what determines this is something called Snell's law, okay? So, Snell's law is what makes refraction occur. Okay, so I hope you can understand my drawing here. So C1 and C2, and why I drew theta 1 and theta A, I don't, oh, A and B, I see what it is. Okay. So theta, okay. Let me get a couple things straight for you here. I've changed the boundary now so it's horizontal, okay?
Oh, okay.
The measured angle is now vertical, the normal line is now vertical, okay? Theta 1 is our incident angle. Call it theta I. I can say I, because ones look like eyes. I just forgot the dot. All right.
You can like think of it of angle of incidence. So.
Yep. So that's going to be theta sub I. Now, theta A is the angle between our transmitted beam. I'm going to switch you over to the other thing here. So theta A is this angle between the transmitted beam is narrower, smaller angle than theta I, right? Okay, so let's go back. Theta B is the transmitted angle is much larger than the incident angle, okay? So let's go back again. Okay. Remember, C represents your speed of your different media. If C1, the speed in this first media, the incident media, is less than the speed of the transmission media, then the incident angle is less than the transmitted angle. If C1, the speed in C1 is greater than C2, then the incident angle is greater than the transmitted angle.
Angle of incidence
Yeah.
is greater than.
Hmm?
Theta is the transmitted angle.
Theta is both the incident angle, theta 1, over here is the incident angle, and theta A or B is the transmitted angle, okay? And A corresponds to this situation up here at the top. C1 is less than C2. B translates to this one, where C1 is greater than C2. And theta 1 and theta 2, theta 1 is the incident angle and theta 2 is one of the two, A or B, of the transmitted angles. Now, the easy one, of course, is situation 3. If the speed of sound is the same in both media, then there's no change of angle and it goes straight, even if it's oblique. Okay? And if you want to have fun with this, just plug some numbers into Snell's law and calculate the different angles. stick with learning that part up on the top left. Okay?
Are we gonna be test on plugging numbers in?
You'll be tested on, so the type of testing you'll get is, if, let me see if I can get my cursor over there. Where's my cursor? Okay, there it goes. If this is your incident angle, okay, and if I give you a speed of both media, you'll have to be able to predict whether the outcome will be here, or straight. Okay? Now, how do you do that? Well, if the speed is lower in the first one, then the incident angle is less in the transmission, right? So this angle is less than that angle. This angle is more than that angle. So by applying these three rules up here, you can determine exactly where that thing's going to come out. Okay? Yeah, there's lots of examples of refraction that you can look up on the internet. Now, why is this so darned important? What time is this class over anyhow?
It's on the feed.
Oh, yeah, we still got 25 minutes, don't we? Good. So this is important because a couple of things. One is known as the duplicated aorta, but that's not so important. But this is more important here. Refraction can sometimes cause loss of signal. Okay? So here we have obstetrical ultrasound with a fetal head, and you can see these portions of loss of sound coming off of this fetal head here because the bone is really hard compared to the soft tissues around it. And so what does that tell you? It tells you that there's a big difference in speed of sound between the bone and the soft tissue. So when the sound hits that bone, it's refracted a lot, and it just disappears. Okay? So this is known as a critical angle artifact. Remember I said critical angle was the loss of signal just due to refraction. Well, this is it. So when you see these round structures and you see shadowing along the sides, it's because of what's called critical angle, and that's refraction, and the sound is just simply lost. It's gone bye-bye.
How do you correct it?
Change your angle of your transducer. So, but this is a round structure, so if I want to see what's in this wedge-shaped area here where there's no signal, yeah, I'm going to have to bring my transducer over at an angle, and I'll see that, but I'll lose it somewhere else, won't I? Yeah. So there's nothing you can do. I mean, if it's happening, it's happening. Okay. Hmm?
Sasha has a question.
Go ahead.
Is this where a crossbeam, does that help this?
Yeah, this is where crossbeam will definitely help you. But we haven't got there yet. But, so she's asking about compound imaging. Yes, that's where you would turn on your crossbeam to help see that area. But there's some problems with that too, and we'll get to them. Yeah, question?
Would you annotate that you have that going on, or?
No, so she asked if I would annotate that I saw critical angle artifact or I saw loss of signal due to that. No, I wouldn't. Because anybody reading these images better be smart enough to look at it and go, yeah, of course. That's refraction error. You've lost signal due to refraction. Now, what you do need to be able to do, rather than annotate, is exactly what Sasha said, how to correct for it if you need to. Okay, and that's compound imaging or something like that. And we'll get to that at a later date. Okay, so here's some examples of shouldn't say diffraction, it said refraction. I gotta fix that one. That one's bothering me.
Well, that's because it's totally.
Yeah, it's totally different. I'm going to call autocorrect on this one. All right, let's see here. Okay, so here is what we have to have. We have to have, for refraction to occur, and if you look at this picture on the bottom left, refraction is certainly occurring. There we go. Cursor. Okay, so refraction is certainly occurring. There is oblique incidence, and there is a difference in speed. So the light is going through the air at a different speed than what it's going through the water. We get refraction. If we don't have oblique incidence, we get what's happening up here in the top right. Okay? Now there's some magnification occurring, but we don't have oblique incidence, so the pencil still appears straight. It's not refracted. And in the bottom one, the bottom right, we don't have a difference in speed. The water is not there, so there's no refraction again. Okay? So the takeaway has got to be, at the end of the day, for refraction to occur, there must be a difference in speed and there must be oblique incidence.
So are you saying like, instead of saying a difference in medium, are you just saying difference of speed because the same organ can have different
Yeah.
textures?
So I'm saying difference in speed because that's what causes refraction. Okay?
Like, could one part of an organ be different than the other?
Yeah, you could have fat within a liver or something like that, causing some differences. But more importantly, if we think back just a few minutes ago when we had reflection occurring, reflection occurs because of the difference in impedances. Okay? Now impedance and speed is related, but they are not the same. So you could technically have two media that are different with the same speed, right? And that would not have refraction, but it would have potentially some reflection. Okay. All right. So again, here's another summary for refraction. If the speeds are equal, there's no change in direction. If speed 1 equals speed 2, no change in direction. Okay. If speed 1 is greater than speed 2, then we see a change in direction of the transmitted sound beam. And in this case, the angle of transmission is less than the angle of incidence. Now, if you remember back where we had those 3 rules, this is showing you rule number 1. Okay, and then the last incidence here is if the speed in the incident media is less than the speed in the transmission media, then the angle of incidence is less than the angle of transmission. I don't know if people are like leaving to go to the bathroom or if they're just going to throw up. I don't know. I keep seeing people go out either door. It's like, maybe they're just sick. I don't know. Yes, ma'am.
Okay, so I'm just trying to wrap my head around it. So just taking the bottom right for a second.
Okay.
So speed one, it's
Mhm.
going at the initial incident, and then speed two is faster. That's why it goes so much. Is that why it goes down? It's going that much quicker through it. And then when it's higher, it's taking longer to get through the material.
Yeah, it's changing direction. Okay. So let me try to draw a picture of what's happening here. So let's put our boundary layer in here, and I'm going to pull this up for you. All right. And this is our normal line, okay, that we're going to measure from. We always measure from the normal. And for some reason, a few years ago, I settled on making the normal line always green. So when I'm doing this, that's what it is. Okay. Now, here's our incident beam, right? But I'm going to draw this with some size to it, okay? So that we see the part of the beam that has reached the, let's undo that. That has reached the second media, yeah. So let's label the media so we know what we're doing here. 1 and 2, okay? All right. So this part of the beam right in here has reached the media before the rest of the beam over here, right? Okay. So if media 2 is faster than media 1, right? What will happen is this part of the beam will start moving faster. That should make sense. Right? So now it's going quicker. Okay. And this part that hasn't quite reached the change in media yet is lagging behind. And so what it causes is it causes this to lag behind, and so we get a change where it starts moving at a greater angle than it was. Okay? So yeah, you're absolutely right in that it's caused from the beam hitting it and going faster. But parts of the beam don't go faster until they get to the boundary, and so that causes the change in direction. Okay? Another way to think about it, and this is what a lot of people like to use, how many of you have driven your car like really fast into a bunch of mud? Okay? Or a puddle of water, you know. As soon as that wheel hits the slower media, the water or the mud, it's going to pull you in that direction, right? Yeah. So that's the same kind of thing. It's going to cause you to change your angle of motion.
Because some of the wheels are on that other median.
Right.
And the other one is not yet, so
Right.
it's-
And so the idea might be like driving from mud into ice or something, right? It's going to cause you to change direction. If you hit it straight on, you don't change direction because everything hits at the same time. So we have to have an oblique angle, plus we have to have a difference in speed. You know? So that's exactly what's going on.
So like with light you get diffraction, does that something happen with sound?
So with light you get refraction.
No, like where you get the colors of the rainbow, because it's all different?
No, so let's go back to that picture because that was on here. Okay. So she was asking, why does the light spread out? And she's calling it diffraction, but it's not really diffraction. It's actually refraction. And it's doing the same thing. So the light is all coming in at the same speed and it's hitting a new media and changing direction. Well, what happens is the light has different wavelengths, okay? So the blue light has a shorter wavelength than the red, and when it hits the different media, it actually refracts more than the red, okay? And so that's why light refracts and spreads out, is because all those colors of the rainbow are hitting at different angles, and that's what causes it to change. So the wavelengths are different sizes, and so it's actually hitting at different angles. Not really the speed difference, but the angle difference.
So we don't really get something like that with sound?
But we do get something like, we get a change in direction with sound, but we're using a single frequency.
Got it.
Okay, so it's a more coherent change of direction. Yeah. So we covered a lot today. Okay, reflection. The percent reflection is just simply the difference of impedances squared, okay, times 100%. Amount transmitted is simply 100% minus whatever was reflected, okay? With reflection, whatever the angle of incident is the angle of reflection. Okay. Angle in equals angle out. With transmission, it depends on several things. It depends, one, is there a difference in speed of the media? If there's no difference, then it just goes straight. Okay. Second thing it depends on, is media 1 faster or slower than media 2? Okay. If there is a difference in speed and there's a difference in angle, an oblique incidence, then we get refraction. So it only took 1 minute to summarize this entire lecture. So it's really not that much when you think about it. But I know it's all new language to you, and so it is a lot. So, you know, you've got reflection, transmission, angle of incidence, normal angles, the whole perpendicular, orthogonal, right angle, 90 degree, and normal, right? You gotta know all that. You gotta remember the C1 is less than C2, then theta 1 is less than theta 2. C1 is greater than C2, theta 1 is greater than theta 2. If C1 equals C2, then theta 1 equals theta 2, right? And then you have to know where to put your thetas and stuff. Yeah, you had a question.
So is the black line, is that the impedance?
So in this case that we're showing you, the black vertical line is the boundary.
That's the boundary.
That's
And
the
then the
boundary.
green one is the
The
normal?
green one is the normal, yeah.
So kind of what I'm seeing is that if, like, speed 1 on this left side, when it's hitting the middle, it's going to end up being a greater angle on the other one, because this is greater and it's greater.
So-
The other one's less, if you're on a smaller one, then it's just straight.
Measure your angle from the normal.
Okay.
This is definitely smaller.
Oh, okay, so I was looking from the black line to
I
the
know,
middle.
that's the mistake most people make.
Okay.
Is, and that's why I kept going over and over. I said, measure from the normal, okay? I kind of emphasize that a lot, and that's because that's the mistake people make, is they measure from the boundary, not from the normal line, okay? So that's a really good point. Yes, it looks bass-ackwards because you're measuring from the wrong line, yeah. And so, yeah.
I kind of like, is it bad to look at this and think of it as pretty much, so like you got, you know, your water and oil and you just have something going this direction and all of a sudden it can't go as hard but it's still going down, so that's why like when it hits that denser thing, the angle.
Well, you're
goes up a
thinking of it
little bit.
absolutely correctly.
like, it's not bad to look at this and just think, oh, well, it's trying to go this way, but it's going a little bit slower, so the angle, or like this one, it's like, it went boom. It's like,
You can think of it that way. That's fine. As long as you're recognizing that if there's a difference in speed of the media and an oblique incidence, it will change direction. Okay, that's half of what you need to know. The other half is, well, does it change direction this way or that way? Okay, and that's where you have to know these greater than or less than symbols and keep those straight. And where you're measuring from, keep that straight.
do you have practice?
Hmm?
Do you have any, like, is there any websites or anything
Oh,
or you
yeah.
go to for like practice?
Yeah.
Oh, you
That's,
can,
like,
you
like,
can
we
go to a
practice, like-
website and look up refraction, and there's all kinds of things. You can change the speeds and you can do all kinds. Now, most of it deals with light, but yeah, you absolutely can find that on the web. Absolutely. Yeah. Tired.
No, I'm thinking.
Okay. Sure, a few people are thinking today. I knew chapter 6 was originally voted. And so, we got through it okay.
So I was saying diffraction is when dealing with light, is that where you go around the angle and it either gets smaller, like opening the door and it goes around the corner or something?
Yeah, more or less.
Yeah.
Or like sound waves going through water, going smaller?
So the classic diffraction for light is the split lens, or the split, lens experiment, where light goes through and then it diffracts into angles. Maybe that's,
Yeah, I think it is. Like if you're thinking of like the ocean waves coming in real
yeah,
big and then it has
the
a
double
small,
slit experiment, yeah.
yeah, it has like a small hole to go through.
Yeah, that's, we do that, and then we end up, if we do it correctly, we end up with Schrodinger's cat.
What? Oh, what?
Oh.
I know, but I didn't want to have you until we finish this.
That's funny.
Yeah. So this is diffraction, this kind of thing here is the light is moving.
Oh, we can't see.
Oh. I'll just change that
Like,
real quick.
yeah. Like if this was light and not sound. Like it'd be like.
I'll make it visible. So this is your typical diffraction experiment. This is called the double slit diffraction. This is more the classic picture of it right here. So the light hits these little slit openings and then it diffracts. So that's diffraction, and we're not even dealing with diffraction these days today. We will deal with diffraction soon, but not like this. This is physics. You don't need to know interference patterns. You don't need to know that anything.
How many chapters is it gonna be in two? Like, what are we?
Gosh, I hope we can get to chapter 10,
Okay, so.
because that's where we want to be for the next test.
Okay.
So 6.
Yeah, chapter 6 is like 2 chapters and 1 chapter.
Yeah, it's kind of like a couple.
Decimals and then this reflection and diffraction on each side.
Any other questions?
My notes are all back.
Those are
I thought we were done. And then
I know, what was the second one? Normal and those other ones.
90 degrees.
Oh, so it's writing and then
We're trying to get the smart stand for again.
Perpendicular, orthogonal,
It's like.
Okay, perpendicular, 90 degrees, so like,
Are we starting chapter 7 on Friday? Study group, I was thinking anybody. Are we starting chapter 7 on Monday?
I'm not gonna lie, probably.
I thought that's what we were doing tonight, because none of us actually started on the power side, so I was like, so I'm just gonna rip those down, just in case of any It's okay, I was just like, wanting to make sure before I did that, so I didn't see you.
didn't realize that I hadn't closed the updated version.
There's like like 10 slides.
I'm sorry, I would like to, but I honestly don't realistically see it happening.
All right, I better get out of here because I know that Miss Marla's coming in.
Oh my god. Oh yeah. Yeah.
okay, so I love my babies. I'm horrible.
So we're gonna do like that. But we're gonna do it. Oh wait, Haley, this is your charger. So I guess it's more gonna be kind of.
I'm like worried about passing.
I'm gonna figure out what to make this stand out.
So now I'm like at 64, so I'm not passing right now. And so if I like score higher,
You can keep this. I do not want that.